Today's subject is crustal deformation and mountain building. We will first start by talking about rock deformation's definition, its causes, and some terms related to the rock deformation. The general term of rock deformation refers to all the changes in the shape or position of a rock body in response to stress. Any kind of structures and features resulting from the forces generated by the interactions of tectonic plates will be defined by rock deformation. And we use specific words depending on the properties of those deformations, such as folds, faults, or joints. When we talk about rock deformation, the first thing we will need to define is going to be the stress. Stress is the force that deforms rocks. When the stress level acting on a rock exceeds the strength of the rock, deformation happens. And this deformation can happen by flowing, folding, fracturing, or faulting. When we talk about stress, we usually talk about two different types of it. The first one is the confining pressure, and the second one is differential stress. Confining pressure actually comes with the depth of the rock body, and it refers to the pressure applied from all the directions to all the surfaces of the rock body, which is sort of a squeezing pressure. Something may happen like under seas. And differential stress will be more involved in the directionality. When we talk about differential stress, we will be talking about three different types of it: compressional, tensional, and shear stresses. For defining these three different types of differential stress, we should look at a cube of rock as a starting point. So if we assume that this is our undeformed rock, once we apply compressional stress, we will be applying stress from both sides of this cube of rock by pushing it towards its center. In this case, this compressional stress we are applying will cause to shortening along the stress direction and lengthening or thickening in the perpendicular direction. There is also tensional stress. In this case, this time we'll be applying pulling forces from both sides of this cube of rock. And this actually will lead to a stretching shape. And we will have elongated distances or longer lengths along the stress direction and shorter length or shortening along the perpendicular direction. And the last type of differential stress is going to be shear stress. In this case, we again are applying two directional forces on both sides of our cube of rock. However, in this time, their directions are going to be opposite ones. And shear stresses usually lead to either sliding or tearing kind of deformations. Strain is defined as the change in rock shape caused by differential stress. So to get a little more detailed understanding of this, let's look at this deck of cards. When we mark a circle on the side of this deck and then apply two forces in two different directions, one from top towards right and the other one from the bottom of the deck towards left, we will see that the shape of the deck is going to change by following these different stresses. And then the circle we marked on the side of the deck is going to change to more elongated ellipsoid kind of shape. By actually looking at this shape, we can identify the directionality and intensity of the stresses we are applying to this deck of cards. And any kind of stress we apply to these objects will end up with strain or deformation. We have two different types of deformations. The first type is the one that will bounce back, and the second type is going to be forever. There's no turning back. Let's first talk about the type bouncing back. We call it as elastic deformation. In this case, when we remove the stress that we applied on the rock body, the rock itself is going to return to its original size and shape. In this case, we call this kind of deformation as elastic. And the closest example for this can be a rubber ball. When we have this perfectly circular rubber ball and apply when we apply stress to this ball by squeezing it or pressing it from both sides, we will see that its shape is going to turn to more ellipsoid elongated shape. And by again looking at this shape and its ratio to the original shape, we can identify the types, the directionality and intensity of the stresses we apply to this ball. And once we remove this stress, we will see that the ball is going to bounce back to its original perfectly circular position for a perfect circular shape. So we call this kind of a deformation as elastic deformation. There is also types of deformation which won't come back, which won't bounce back. In this case, we may either have brittle deformation, which will occur instantaneously in very short time, or we can have ductile deformation. Ductile deformation is going to happen in long times. So for brittle deformation, we can have the example of a porcelain plate, which will break and there's no turning back. Or for ductile deformation, we can have a roll of dough will be squeezed in between two books. The shape of dough is going to change to more like flat, elongated shape. But once we remove these books, its shape isn't going to bounce back. But the change in shape, the deformation itself, is going to happen in a long time or slowly. Now let's talk about the factors affecting rock strength. We have four main factors: temperature, confining pressure, rock type, and time. Temperature is actually a factor affecting the behavior of rock by either being ductile or brittle. So when we have higher temperatures, the rocks under those temperatures will act more ductile and lead to more ductile deformation after being stress applied. On the other side, when we have cooler rocks, the deformation is going to be more brittle. So if we just talk about the geothermal gradient, we can say that the deeper located rocks are going to deform more ductile, and the ones being closer to the surface of the earth are going to deform more brittle. And there is this confining pressure, which actually acts really interestingly. Once we have confining pressure applied to rocks, it is going to be squeezing the rocks from all the directions, and it makes them stronger. So it will be harder to break or change their shapes. So increasing confining pressure is going to make harder to break a rock body. When we get deeper rock body locations, it's going to be harder to break them because confining pressure increases by the depth. And rock type is another important factor. When we have crystalline or igneous rocks, we generally will see more brittle deformation. On the other hand, when we have sedimentary or metamorphic rocks, we will observe more ductile deformation since they have some zones of weaknesses, which we will see more slower changes along those weakness zones. And time is the last important factor. Depending on the time period of those forces applied, we will see the resulting deformation either being brittle or more ductile. Longer periods of time will lead to more ductile deformations. Now let's talk about the rock structures formed by ductile deformation. Our first example is going to be faults. Faults are often defined by undulations, wave-like undulations, and they likely come out from compressional stresses. So when we push the rock body from both sides towards its center, we will see that its width is going to get shorter and its thickness is going to increase. And when this is happening, the rocks are going to bend into a series of wave-like undulations. We called these undulations as faults. We also have some specific names by looking at the geometries of these different faults. First of all, we have these two types we call as anticlinal and synclinals. Anticlines are upfolded or arched sedimentary layers, and synclines are downfolded or troughs of rock layers. And when we look at this picture, we will see that here we have anticlinal structures and synclines. Anticlines are more like down-looking U-shape, and synclines are the reverse, up-looking U-shape. In this case, when we have the erosion happens, the middle part of this structure is going to get exposed the older rocks. These are the older rocks in this layer, in this series of layers, and this darker color is the younger rock. And because of its shape, the center part is going to be the older rock, and on the sides we will have younger rocks being exposed. And with synchronize, it is going to be the reverse. In this case, the center part is going to expose the younger rocks, and on the sides we will see the older ones. By looking at the different geometric properties of these structures, we also call them with different names. So when we have both limbs of this antagonine or synclinine being equal or symmetrical, we call it as a symmetrical fault. And sometimes one of these limbs may be steeper than the other one. In this case, we will call it as asymmetrical fault. In some cases, we may get some faulting or breaking or extreme ductile deformations in these rock structures, which actually will lead this older material moving up over the younger material. We call this as overturned fault. In case of overturned fault, we will see very old material on top of the youngest material. Another type of the rock structures formed by ductile deformation would be domes and basins. Domes are upwarp circular features, so they will more look like a hill. And basins are downwarp, so they more will look like bowls. By looking at this figure, we can identify different properties of domes and basins. Here on the left, we see a dome, and the layers would look like this. And when we have this structure being eroded, this middle part, the central part, is going to show the oldest material. And we will have the youngest stuff going on the sides. So the center part of a dome is going to be the oldest layer, and the edges going out towards the outer edge of the circle is going to be the younger material. And the reverse thing will happen in case of a basin. Basin is going to look like a bowl. And then once we have the top of it being eroded, the stuff we will see in the middle is going to be the youngest ones, because see, the youngest layers are going to be sitting on top and the oldest ones were just curving upward. So these parts on the edges of the circle, outer edges of the circle, will be more older material. And then another type of rock structure formed by ductile deformation will be monoclines. Monoclines are large step-like faults, and it actually come out from normally horizontal laying sedimentary layers. So the blocks of basement rocks are going to be displaced upward, and then the ductile sedimentary strata will go down over them. So here we see an example. So over here we normally have are perfectly horizontal layers at the beginning. But then there'll be this fault in the basement rock or the base rock. And this left side of the fault is going to move upward and the right side is going to go down. And in this case, this upward motion is going to push this side of the sedimentary layer up towards high. And when they get high, that means they will more keen or more open to erosion. And once that happens, the top part, the younger part of the sedimentary layers are going to be gone, and we will see the older stuff down in here.